Okay, in example 4 here, we're going to define, we're going to let pi equal a projection from R3 to R2. So it's going to be onto the XY plane. So it's just a projection onto the XY plane. And so to give a matrix representing this map, we first have to fix some bases. So here's a basis from the domain, and here's a basis, a basis from the codomain. Now, for each vector in the domain's basis, we want to find its image under the map. Again, that's easy to do. Again, just verify that. So under this mapping, right, it's just a projection, right? So it's easy to find. We're just getting rid of the z component. So this reduces to 1, 0. This reduces to 1, 1. And this reduces to negative 1, 0. Okay, so that's pretty straightforward. So now, again, what we just did was for each vector in the domain's basis, we found its image under the map. So we found that. Now what we want to do is we want to find the representation of each image that we just found with respect to the codomain's basis. So again, we can write this as a linear combination of these, and we can find that representation as 1, negative 1. Okay? Because if we take 1 times this plus negative 1 times this, we get this. So that'll work. So again, pretty straightforward what we've been doing. And then the representation with respect to D of this image is equal to this. And the representation with respect to D of this image is equal to that. So that's the next step, right? So we went from here to here, here to here, okay, for each one. Now finally, what we're going to do is we're going to join all of these representations to get our our matrix that represents pi, the map, with respect to B and D. So now we've got that representation. Okay, so now we can illustrate the theorem, theorem 1. So I'm going to just leave those up there. Okay, now we keep again, we're just adjoining this, this, and this to get our representation matrix. Okay, now what we can do is we could take a vector, right? Let's say 2, 2, 1, and we could take pi of, let's say, 2, 2, 1, and that's going to give us 2, 2, and then we can find the represent the domain vector with respect to the domain's basis, right? So now we can write the representation. So let's do that. Let's write the representation with respect to B of what? 2, 2, 1. And what would that representation look like? One times this one, plus 2 times this one, plus 1 times this one. So it's going to be 1, 2, 1. Because if we get 1, we'll get 1 plus 2 is 3 minus 1 is 2. And then we get 0, 2, 0. So that gives us 2. And then we get 0, 0, 1. So that'll work. So 1, 2, 1 works. Okay, now we're going to get the matrix product, the matrix vector product. Now that we have this, and we've got our representative matrix, now we're going to take our representative matrix with respect to B and D of pi times the representative matrix with respect to B of 2, 2, 1, which is going to equal what? We're going to get 1, negative 1, 0, 1, negative 1, 1. And we're going to multiply that by 1, 2, 1. So again, this is a 2 by 3. This is a 3 by 1. And so now what we're going to get is we're going to get we're going to get 1, 1 plus 0 plus negative 1, and then we're going to get, oh, hold on a second, let me just make sure I'm doing this right. Yeah, and then I'm going to get negative 1 plus 2 plus 1. And that's going to give me 0, 2. Oh, with respect to D. So what is this? This is what? Again, this is just the representative with respect to B of what? Pi of 2, 2, 1. Equals. Okay, sorry if it's a little sloppy. Now, we're not done yet. Now we're expanding this into a linear combination of vectors from D. What do we get? Okay, now we're going to take 0, 2, and we're going to write it as a linear combinations of the vectors in D. Zero times 2, 1. Zero times 2, 1. Yeah. Yeah. Take these two, 0 times 2, 1, 2 times 1, 1. And that'll give us 2, 2. And this checks that the map's action is indeed reflected in the operation of the matrix. And now we will sometimes compress these three displayed equations into one. And so sometimes we'll express it this way. So we start with 2, 2, 1, which is equal to 1, 2, 1 with respect to B. Okay, and then with this transformation, we get 0, 2 with respect to D, which equals 2, 2, which is the same thing we got, remember? When we apply pi to 2, 2, 1. So now we have two ways to compute the effect of projection. The straightforward formula that drops each three tall vectors, third component to make a 2 tall vector, and the above formula that uses representations in the matrix vector multiplication. The second way may seem complicated compared to the first, obviously, but it has advantages. And so what we're going to do is, looking at the next example, shows that for some maps, the new scheme simplifies the formula. See you next time.